Hello and welcome. My name is Noah Deer, and this is Lesson 19, Triple Integrals in the Math 254 Vector Calculus 1 class at Portland Community College. We are going to start by looking at a triple integral computation. That is, we're going to formulate what a triple integral represents as far as a hypervolume over an XYZ three-dimensional space domain. So we'll use a Riemann sum to set that up and look at its formal definition. We will then go ahead and do some review of how we use a double integral to find the area of a given domain. We'll then look at how we can extend that to finding a volume using a triple integral. And then we will look at finding triple integrals of functions in three variables. So if I have w equals f of x, y, and z, then we take a triple integral of that to get a hypervolume over the given domain in x, y, and z. And then we'll do something that we're actually going to get into more in Lesson 20, but we'll see a triple integral that's easier to look at using polar coordinates, where the x and y's we convert to r's and thetas, and how we use something similar to what we did in double integrals with the switching to r dr d theta. So we'll get to that here towards the end of the lesson. Let's go ahead and jump in now. We have section 19.1, triple integral computation. So we're just going to practice some of these, and then we'll get into the coming up with the formula here in just a moment. So before getting into definitions and interpretation, let's simply practice computing triple integrals. So if we have the example 19.1.1, evaluate the triple integral, which is the integral from 0 to 1 of the integral from -1 to 2 of the integral from 1 to 3 of x, y squared, z, dz, dy, dx. Then, I'm just going to copy it down here real quick. Integral from 0 to 1, that's in the x direction. Then we have the integral from -1 to 2, that's in the y direction. And then the integral from 1 to 3, that's in the z direction, of x, y squared, z, dz, dy, dx. So we start and essentially do this inside integral with respect to z first, so a partial antiderivative with respect to z. I'm going to copy down the 0 to 1 in the x direction and the -1 to 2 in the y direction. Here, as I take the antiderivative with respect to z, I'm going to get 1/2 x y squared z squared, and we want to evaluate that from 1 to 3. Keep in mind that these bounds are with our z values, since we were taking the antiderivative with respect to z. Copy down the dy dx, then this equals the integral from 0 to 1, which is in the x direction, the integral from -1 to 2 in the y direction. When I plug in 3 and squared, I get 9 minus 1 squared. Keep in mind that 1/2 xy squared is all considered a constant, so this is 1/2 xy squared times 3 squared minus 1 squared inside parentheses dy dx. Let's go ahead and start a new line here. Moving over to my next column, this equals the integral from, actually, before I do that, let's see, so 3 squared minus 1 squared, that's 9 minus 1 is 8, and then multiply it by 1/2 is 4, so I'm going to just pull that 4 in front of everything. We have the integral from 0 to 1 in the x direction, the integral from -1 to 2 in the y direction, and we have now just xy squared dy dx, because the 3 squared minus 1 squared times 1/2 we pulled out as the 4 in front. So this then equals 4 times the integral from 0 to 1 of 1/3 xy cubed when I take the antiderivative with respect to y, and I'm going to evaluate that from -1 to 2, and then, oh, I'm sorry, I totally messed this up. Let's backtrack a little bit. Wait, no, I didn't. I'm second guessing myself. Yeah, so then we'll do dx last here. So then this I'm going to plug in 2 for y and cube it, and then subtract -1 cubed. So this is going to equal 4/3, pulling out that 1/3, times the integral from 0 to 1 of x times 2 cubed minus -1 cubed dx. So this equals, let's see, we get 8 minus -1 is +1, so that's a 9. 9 divided by 3 is 3, times 4 is 12. So we get 12 times the integral from 0 to 1 of x dx. So this equals 12 times 1/2 x squared, evaluated from 0 to 1, equals 6. Okay, so pretty straightforward. We essentially do the same thing that we did with our integrals, our double integrals, except for now we just have a third integral and we just do it step by step, one at a time. So the next one's going to be a little bit more complicated. It's an exercise for you, so I do want you to go ahead and give this a shot. Take some of the stuff that we learned using the double integrals, where we have to evaluate to some bounds that are functions themselves, and plugging those in. So use that knowledge that you already have and try and work through taking this triple integral. Exercise 19.1.1, evaluate the iterated integral, the integral from 0 to 1 in the z direction, the integral from 0 to z in the x direction, the integral from 0 to x plus z in the y direction of 6xy dy dx dz. Go ahead and pause the video. And then come on back here once you're ready, and I will work through the solution with you. And we're back. Okay, so I just went ahead and copied down the original problem. We have the integral from 0 to 1 of the integral from 0 to z of the integral from 0 to x plus z of 6xy dy dx dz. So we take the antiderivative with respect to y first, and we get that this equals the integral from 0 to 1 of the integral from 0 to z of 3xy squared, evaluated from 0 to x plus z, dx dz. We plug in the x plus z for y, because these were y values. So we get that this equals the integral from 0 to 1 of the integral from 0 to z of 3x times, parentheses, x plus z quantity squared minus 0 squared, close those parentheses, dx dz. This then equals the integral from 0 to 1 of the integral from 0 to z of 3x cubed plus 6x squared z plus 3xz squared dx dz. What I did was I FOILed out the x plus z squared and then multiplied the 3x in to get that. We're now going to take the antiderivative with respect to x, so that we get equals the integral from 0 to 1 of 3/4 x to the 4th plus 2x cubed z plus 3/2 x squared z squared, evaluated from 0 to z, which are x values, dz. Moving over to the next column, we get that this then equals the integral from 0 to 1 of 3/4 z to the 4th plus 2z to the 4th plus 3/2 z to the 4th dz, and that's just by plugging z in for the x's in the previous line, and when we plug in 0 for x's, that will go away, so we're not going to have that minus term here. I went ahead and added up these terms because they're all like terms with z to the 4th, and we get that this equals 17/4 times the integral from 0 to 1 of z to the 4th dz, which equals 17/4 times 1/5 z to the 5th, evaluated from 0 to 1, which equals 17/20. That's it. So yes, this one was a little bit more involved than the previous because our bounds in the y and the x directions were not just numbers, they were functions themselves. So this is y as a function of x and z, and then this is a function x as a function of z here. And so we just need to go ahead and plug those in as our upper bounds and work through the integral just as we would otherwise. So hopefully you've got that sorted through. Go ahead and slow it down, rewind as you need to. But I'm going to go ahead and move on to the next section, 19.2, area via double integrals. Okay, so let's consider the volume between the surface f of x comma y equals 1 and the xy plane over a domain D. we calculate such a volume via the double integral double integral over the domain D of 1 dA, and that actually ends up equaling the area of the domain itself. And the reason that this is, let's go ahead and take a look at this graph in GeoGebra, figure 19.2.1, the area equaling a volume. Go ahead and go to this. And if we recognize that the volume is simply going to be the area of the domain times the height, which equals 1, we get that the volume equals the area of the domain times 1 just equals the area of the domain. Now technically, if we were doing units, we would need to realize that the volume is a 3-dimensional units and the area is a 2-dimensional units, but computationally the number works out to be equal for the area and the volume. So let's go ahead and apply that in the following example, 19.2.1. Use a double integral to find the area of the region bounded by y squared equals 2x plus 6 and y equals x minus 1. Let's do the second one first. That looks a little bit quicker and easier here. So x minus 1, we go down 1, and then we have a slope of 1. So we get this line here. Best line here, but actually I'm just gonna, okay, so that looks a little bit better. This is y equals x minus 1. My y squared equals 2x plus 6. I'm actually going to solve for x here. I've got 2x equals y squared minus 6, so x equals 1/2 y squared minus 3. So this is a parabola that opens in the positive x direction. It's shifted back 3 units, and it's compressed by 1/2 in the y direction. So I'm going to have here, and then what would be 4 is now here, and then if y, I think, this, I believe, then 3, and then 5, 2, 3, 1, 2, 3, 4, 5, to there, and 7, 1, 2, 3, 4, 5, 6, 7 is going to be here at this point. Here we have x equals 1/2 y squared minus 3. This is the point -3, 0. Then we have the point -1, 2. And then I'm not going to worry about labeling that point. This point's more important. This is 5, 4. My scale on my axes here. So if we were to find, if we wanted to set up a double integral in order to find the area of this, we would say, we could do this a couple different ways, but I want to integrate in the x direction first. Oh, I need to label this point -1, -2. That's definitely going to be a key point here. So if this is my x lower bound, which we know is 1/2 y squared minus 3, then this is my x upper bound, and so that's going to be y plus 1, going ahead and solving for x and y equals x minus 1. So if I do that first, my lower bound is 1/2 y squared minus 3, my upper bound is y plus 1, and the y direction, we're going to go from -2 to +4 at these 2 points of intersection. So the area equals this double integral evaluated over 1 being the z value, the height. So the volume of this prism is going to equal the area of the region here. And so this is going to be dx dy. So this integral is the integral from -2 to 4, and then we have that the antiderivative with respect to x evaluated from 1/2 y squared minus 3 to y plus 1, and then dy. So this equals the integral from -2 to 4 of y plus 1 minus 1/2 y squared minus 3 dy. And here we actually see what the single integral that we would use in order to find the area of this domain here. So if you think back to second term calculus, you can find areas of regions like this using a single integral. We would have this upper bound as x upper equals y plus 1, the y lower bound, or the x lower bound equals 1/2 y squared minus 3. And we would do the subtraction of those to get us in between them to get the area of this region. So this would be the single integral that we would set up, and we end up getting it as one of our steps in this double integral. So let's go ahead and simplify this here. I'm going to go up to a new column. Just don't want to get too low on the page here. I think I got the room. So this equals the integral from -2 to 4 in the y direction. Let's do this -1/2 y squared first, and then we'll do a plus y, and then a 1 plus 3 is plus 4 dy. So this equals -1/6 y cubed plus 1/2 y squared plus 4y, and we evaluate this from -2 to 4. So then I get 4 cubed is 64, so -64 over 6 plus 16 over 2 plus 16 minus -2 to the cubed, -2 to the third is -8, and then there's another negative, so that's a positive 8 over 6, and then plus 4 over 2, and then minus 8. Alright, let's put these together. -64 minus 8 is -72 over 6, and then 16 over 2 minus 4 over 2 is plus 12 over 2, and then 16 plus 8 is plus 24. Let's see, 6 goes into 72 12 times. This is -12 plus 6 plus 24 equals -6 plus 24 is 18. All right. And so let's take a look at the GeoGebra. So pulling this up, we can see here is that region that we had described before, and here is the prism, whose volume is simply that area that we just found times the height of 1, so that the volume of this prism is the same as the area of this domain here. Alright, it's figure 19.2.2, the area between y squared equals 2x plus 6 and y equals x minus 1. Alright, so let's go ahead and move on to the next one. So we want to extend this same concept to triple integrals. So we're going to start by looking at a volume via triple integrals, but we're going to need to talk about triple integrals as a general idea in order to do so. So 19.3 volume of triple integrals. The definition of the triple integral is the triple Riemann sum, so that our iterated integral, triple integral over a domain E of f of x comma y comma z d capital V equals the limit as L, M, and N go to infinity of the sum from I equals 1 to L, of the sum from j equals 1 to M, of the sum of k equals 1 to N, of f of x sub I, y sub j, z sub k, times delta capital V, where delta capital V equals delta x, delta y, delta z, is the change in volume when we cut a three-dimensional domain up into rectangular solid regions. So essentially, if I have some domain, so say this is my domain E in 3 dimensions. My domain is a three-dimensional solid now. And I'm just doing a rectangular solid to keep this nice and simple. If we cut this up in the z direction, and then we cut it up in the x direction, and we cut it up then in the y direction, but then we keep doing this, so then we get like these little cubes here are my delta capital V's, right? The volume of each of these. And as we make these little cubes smaller and smaller, then we get a better approximation to the actual volume of the solid, where generally this volume is not going to be a nice rectangular solid, so we wouldn't just be able to multiply its length by width by height. So if we take this change in our volume and then multiply it by our w value, w equals f of x sub I, y sub j, z sub k, so say we're in here and I'm looking at this bottom left corner, so this is really a little box in here. Okay, so if we're looking at this little cube, and we take the volume of it and multiply it by the w value if we plug this point x sub I, y sub j, z sub k into the function, then we end up getting a hypervolume. So we do this for each three-dimensional subregion of E, and this gives us L times M times N hypervolumes. Each one of these gives us one of them, so if we do L in the x direction, M in the y direction, N in the z direction, then we have L times M times N hypervolumes for each of these. As we let L, M, and N go to infinity, and then delta V will go to 0 as we cut this up into more and more subsections. Then we get an infinite number of infinitesimally small hypervolumes that add up to the total hypervolume over the domain of capital E. So that's the general idea of how we set up a triple integral and how it's defined. It's just an extension of how we set up our double integral and defined that. If we let f of x comma y comma z equal 1 in the triple integral over the domain E of f of x comma y comma z dv, we get the hypervolume h of v, just hv equals the triple integral over the domain E of 1 d capital V equals the volume of capital E, the volume of the region, times 1, which just equals the volume of the domain E. Because the hypervolume's fourth dimensional height is 1, so the hypervolume is equal to the volume of E. Just an extension of what we saw before, where we took the area and multiplied it by a height of 1 to get a volume that was equal to the area, just extending that up one dimension. So we have the hypervolume is equal to the volume of capital E. This is a higher dimensional extension of the concept addressed in the previous section where we found area via a double integral with f of x comma y equals 1. So, example 19.3.1, identify and compute the volume that is given by the integral from negative 1 to 1 of the integral from the negative square root of 1 minus x squared to the positive square root of 1 minus x squared of the integral from 0 to the square root of 1 minus x squared minus y squared of 1 dz, dy, dx. All right, let's work through this. So I'm going to come back. We see that we're doing in the z direction last because dz is the innermost integral that we're going to be dealing with. And that's from z is 0 to z is the square root of 1 minus x squared minus y squared. And if we're starting to feel comfortable with our quadratic surfaces, then we might recognize that this is it's the top half of an ellipsoid. But we'll come back to that in a second. Let's actually look at the integrals in the x direction and y direction. So in the x direction, we're going to be going from negative 1 to 1. But we need to know the shape of the graph, and that's actually given here. So we have the y upper bound equals the square root of 1 minus x squared. This gives us that the y upper bound squared equals 1 minus x squared, or x squared plus the y upper bound squared equals 1, which is just the circle, but it's the top half of this circle with a radius of 1. So I'm just looking in the y-x plane, or the xy plane rather, before I try and put together the entire volume. So here we get the top half. The y lower bound equals the negative square root of 1 minus x squared, and that solves out the same way, so that's the bottom half of this unit circle. Okay. So this is telling us not necessarily what happens when z equals 0. This just shows us that if we were to project this entire volume onto the xy plane, we would see this in the xy plane. But this circle may be, like, we're really looking inside of this, yes? Really, this solid circle is the entire shape, and it may not be in the xy plane. It may be above it, and that's just what we get when we look straight down on this solid that we're trying to find a volume of. So that tells me, though, that I can put 1s and negative 1s in my x and y directions. And if I let then, so we have our z upper bound equals the square root of 1 minus x squared minus y squared. This might be easier to see if we then do kind of the same thing we did above, where the z upper bound squared equals 1 minus x squared minus y squared. So we get x squared plus y squared plus z squared, z upper bound squared, equals 1. And we see that that's just the top half of a sphere, since we're doing just the positive square root here. And it's a sphere of radius 1, so I can just put a 1 in my z direction. And this is going to come down. And so our sphere is going to look something like this. And in the xy plane, in this case it does turn out that when z is 0 we do get that circle. So just drawing that in here. I just don't want you to think that that's automatically what it is, which is why I didn't draw it down here first. I wanted to get an idea of what that upper bound was and where that upper bound intersects with the xy plane. And I'm also thinking about the fact that the lower bound is z equals 0. So when this hits the x, or when z equals 0, that gives us 0 equals the square root of 1 minus, oops, you cannot see that, can you? There we go, better. 1 minus x squared minus y squared. And this solves out to just be x squared plus y squared equals 1. So again, we do get that our z bounds, that the whole shape is really just the top half of this sphere, and it intersects the xy plane at the unit circle. So we're looking for the volume of this region here. So we want to compute the volume of this region. So I'm just going to go ahead and copy down the integral real quick. We have from negative 1 to 1 in the x direction, the integral from negative square root of 1 minus x squared to the positive square root of 1 minus x squared, and then the integral from 0 to the square root of 1 minus x squared minus y squared, and then we have 1 of dz, dy, dx. This then equals the integral from negative 1 to 1, the integral from negative square root of 1 minus x squared to the integral, or to the square root of 1 minus x squared is a positive square root. And then we're going to have the antiderivative is z, evaluated from 0 to the square root of 1 minus x squared minus y squared, dy dx. So this equals the integral from negative 1 to 1 of the integral from negative square root of 1 minus x squared to the positive square root of 1 minus x squared of the square root of 1 minus x squared minus y squared. dy dx. Okay. Now, this integral, we could do a trig substitution here and work through it that way, but this is screaming to me to switch to polar coordinates. So if I want to take this integral, I can switch it to polar coordinates by recognizing that we are going, that in this xy plane, our domain is going to go all the way around in the theta direction. So theta is between 0 and 2 pi, and our radius is going from 0 to 1. So 0 to 2 pi in the theta direction, the integral from 0 to 1 in the r direction, and we'll do the square root of 1 minus r squared, because negative x squared minus y squared is minus r squared. And then this is times r dr d theta. And this is really nice because now I can do a quick substitution of u equals 1 minus r squared. So du equals 2r dr. So we get that this equals the integral from 0 to 2 pi d theta times the integral from 1 to 0 of u to the 1 half times 1 half du. So what I did is I recognized that my inside integral with respect to r has no thetas in it at all. And so I'm able to calculate that separately from the integral with respect to theta. So I pulled the d theta in with the 0 to 2 pi integral. And then here I switch my bounds. If r is 0, then u is 1. If r is 1, then u is 0. And we get the 1 half from the 2r dr in our what we got for du. So this equals 2 pi from the integral from 0 to 2 pi of d theta, and then times 1 half times 2/3 u to the 3 halves evaluated from 1 to 0. And so this equals, well, something seems quite off right now. Oh, yes. So I'm seeing that I'm going to get a negative, and that's sparking my little exclamation point in my brain saying I think I made a mistake somewhere. Hopefully you saw it. Here, when I have u equals 1 minus r squared, du is going to equal negative 2r dr. So I'm just going to move that over, throw on, switch this to red. See my little mistake there. So that's going to make this a minus 1 half, a minus 1 half there. So there's going to be negative pi, negative 2 pi over 3 when I bring these three factors together. 2 pi times 1 half is just pi, times 2/3 is 2 pi over 3, but make it negative. And then we're going to do 0 to the 3 halves minus 1 to the 3 halves inside here, so that's just going to make this a positive 2 pi over 3. And if we think about the volume of a sphere, this equals 4/3 pi r cubed. And since the radius is 1, that's 4/3 pi. And since we only have half of 1, volume of the top half is going to be equal to 2 pi over 3. So that's good. These match up if we do this in two different ways. All right. So exercise 19.3.1. Identify and compute the volume that is given by the integral from 0 to 2 of the integral from 0 to negative x plus 2 of the integral from 0 to 4 minus 2x minus 2y of 1 dz dy dx. So this is going to give us a volume again. Go ahead and sketch out the bounds. I would again recommend in the x and y plane, and then think about the z direction and try and sketch this solid. Note that the x, y, and z values are all from starting at 0. So this is going to be in the first octant. when we look at sketching this, which is why I just have the first octant available for you down here. I'm going to work this out, and once you are ready, unpause the video and I will work through the solution with you. And we're back. Okay, so if I look at, really the key thing here is in the y direction we're going from y is 0, which here we have y lower equals 0, and then we have y upper bound equals negative x plus 2, and then in the x direction we're doing from x equals 0 to x equals 2 at this corner here. So we're looking at this region in the xy plane. Now, to look at this in 3 dimensions, we have z equals 4 minus 2x minus 2y. I'm going to start by drawing now, well, I don't want to quite draw this again. As I said before, this projection may be something that we're seeing above the xy plane, not on it. So if I start by looking at z equals 4 minus 2x minus 2y, if I set x equal to 0, I get z equals 4 minus 2y. So if we get a z-intercept of 4, which is really the point 0, 0, 4, not just the number 4. Then we have the point 0, 2, 0. So with this, we start at z is 4, and we go down 2 over 1, down 2 over 1. So that's going to get us down 2 over 1, and then down 2 over 1, gets us to this y-intercept of 0, 2, 0. If y equals 0, then we get z equals 4 minus 2x, so that's now in the xz plane. We again start with z equals 4, and then we go down 2 over 1, down 2 over 1. So that gets down 2 over 1, down 2 over 1 to this point, 2, 0, 0 on the x-axis. And since this is a plane, z equals 4 minus 2x minus 2y, everything is linear, we can then see that it has to be the plane that connects these 3 points. And then by doing so, we also end up getting that line that we saw in the xy plane above, there from the point 0, 2, 0 to the point 2, 0, 0. And so we are now looking for the volume of this, I'm going to go with pyramid. It's not a regular pyramid. It's not a tetrahedron because it's not a regular shape. We have different side lengths and everything. So we'll just go with pyramid. So the volume of this pyramid is the triple integral from 0 to 2 of the integral from 0 to negative x plus 2 of the integral from 0 to 4 minus 2x minus 2y of 1 dz dy dx. When I take the antiderivative with respect to z, we get that this equals the integral from 0 to 2 of the integral from 0 to negative x plus 2 of 4 minus 2x minus 2y dy dx. This equals the integral from 0 to 2 of 4y, this equals the integral from 0 to 2 of 4y minus 2xy minus y squared, evaluated from 0 to negative x plus 2 dx. Plugging in that negative x plus 2, we get that this equals the integral from 0 to 2 of negative 4x plus 8 minus 2x times parentheses negative x plus 2 close parentheses minus parentheses negative x plus 2 close parentheses squared dx. Foiling and combining all like terms, we get that this equals the integral from 0 to 2 of x squared minus 4x plus 4 dx, which equals 1/3 x cubed minus 2x squared plus 4x, evaluated from 0 to 2, which equals 8/3 minus 8 plus 8, which equals 8/3. So the volume of this pyramid is 8/3. All right. Example 19.3.2. Use a triple integral to find the volume of the tetrahedron capital T that is bounded by the coordinate planes and the plane 2x plus y plus z equals 4. So I'm going to go through and look at if z equals 0, then we get 2x plus y, let me look this up actually, get 2x plus y equals 4, or y equals negative 2x plus 4. So here, if y is 4, and going to change my scale. So this is 2 here, 4 here. Note that, that's important. We have the point 2, 0 here, the point 0, 4 here. And we are going down 2 over 1. So here I've gone down 2 over 1 since the scales are different. And we go down 2 over 1 one more time. And we get this line in the xy plane. Now this is when z is set to 0, so I'm going to go ahead and put a 4 over here on my y-axis and a 2 over here on my x-axis and draw the line between them. And this is where our plane hits the xy plane. So this is also bounded by the coordinate plane, so that means it's bounded by when y is 0, or when x is 0 and when y is 0. So we're looking at this region in the xy plane. And we're also bounded by the z-axis here for the same reason, so we're staying in the first octant, right? And then if I have x equals 0, we get y plus z equals 4, or z equals negative y plus 4. So that's going to start us out with 4 on the z-axis. I want to label these points. This is 0, 4, 0. This is the point 2, 0, 0. And then this point that we're starting at is 0, 0, 4. And the slope is negative 1 in the y direction, down 1 over 1 in the z and y direction. So we go from this point down to there, and then if y equals 0, we get 2x plus z equals 4. So z equals negative 2x plus 4. So here we're going to have the line go down, starting again at the point 0, 0, 4, and then down 2 over 1, and then down 2 over 1 gets us again to the point 2, 0, 0. So we're looking now at a very similar region as what we had before. It is a little bit different. It is definitely stretched in the y direction now by 2, but not uniformly. I mean, it is in like a 3-dimensionally uniform, but it's not just going to be a regular linear stretch. So let's take a look. We'll actually get to see how the numbers play out and compare to that 8/3 that we saw in the previous problem. Let's set up this triple integral now. Let's do in the x direction last. So in the x direction, looking at the xy plane, we're going to go from when x is 0 to x is 2. In the y direction, we're going to go from y is 0 to my y upper bound is negative 2x plus 4. And then in the z direction, we are going, if I solve for z here, I have z equals 4 minus 2x minus y as the plane that is bounding us above. And we take the triple integral of 1 so that we are getting actually a volume instead of a hypervolume. Well, the hypervolume would be equal to the volume itself. Just want to speak accurately here. So this then equals the integral from 0 to 2 of the integral from 0 to negative 2x plus 4. And then when I take the integral from 0 to 4 minus 2x minus y with respect to z, we are going to just get exactly that. And now I take the antiderivative with respect to y. So I'll get the integral from 0 to 2 of 4y minus 2xy minus 1/2 y squared, evaluated from 0 to negative 2x plus 4 dx. So this then equals the integral from 0 to 2. I need to plug these bounds in for y. When I plug the 0 in, that will all 0 out, so I'm just going to worry about the top bound. I'll get negative 8x plus 16 minus, well, I'm going to distribute the negative 2x across, so this will become a plus 4x squared minus 8x, then minus 1/2 times negative 2x plus 4 quantity squared dx. Okay, now I want to go ahead and combine all my like terms. So I'm going to have a 4x squared here, but times negative 1/2 will give me a negative 2x squared. Added to this 4x squared will be 2x squared. Then for my x terms, I'm going to have a negative 8x and a negative 8x makes negative 16x out here. This one's going to be a little bit trickier. Negative 2x times 4 is negative 8x. We'll have two of those is negative 16x times negative 1/2 is positive 8x. It'll cancel with one of these and we'll have just a minus 8x left over. Then for our constants, we've got this 16 out here. When I square this, I'll have a 16 times negative 1/2 is negative 8, plus 16 is just a plus 8 dx. Let's compare this. What did we have up here? We had x squared minus 4x plus 4, so actually exactly half of this. So maybe it does stretch nice as far as the volume goes. Kind of surprises me. I was expecting maybe a square stretch, so maybe a multiple by 4. But let's take a look. Oh, we still have to integrate, so I think maybe I could still be right. Let's take a look. 2/3 x cubed minus 4x squared plus 8x evaluated from 0 to 2. This is going to give me 8 times 2 is 16/3 minus 4 times 4 is 16 plus 16 and then minus 0, and this does equal 16/3, which is exactly double what we had before. Alright, so we just doubled one of the dimensions. Okay, that does make sense as I'm saying it out loud now. We only doubled one of the dimensions. We didn't double the x and the y. So we literally just get a linear stretch of that volume. Since we doubled one of the dimensions, we doubled the volume. All right. Next section, 19.4, triple integrals of functions in 3 variables. So in example 19.4.1, we're going to determine the 3-dimensional domain of the triple integral from 0 to 1 of the integral from 0 to 1 minus x of the integral from 0 to 1 minus x minus y of z dz dy dx. Now we're going to compute the hypervolume over this domain. So by looking at the domain, we're essentially saying what would the volume be, like what is the shape of the volume that we are integrating over, but then the hypervolume is what we get when we integrate with respect, or rather, where we realize that the input function, this is w equals f of x, y, z, is a 4th dimensional output, a w value. And so that gives different quote-unquote heights at different x, y, and z values. Now, this is only a function of z, so just as z changes, the heights change with it. And so we would then multiply all of the volumes by these different w heights to get our hypervolumes of these like little infinitesimal shapes. And then we would add all those up to get our hypervolume of the entire hyper shape. Lots of hyper going on here. Okay, so let's take a look. In the xy plane, we're going from 0 to 1 in the x direction. We're going to 1 minus x in the y direction. So that is just this line right here. And we're going from when x is 0 and y is 0, so we're looking inside this region. This is the y upper bound equals 1 minus x. Now I have my z upper bound equals 1 minus x minus y. So if x is 0 and y is 0, we're at z is 1. And we have a slope of -1 in the x and y directions if we move off of this point in just the x or y direction. So that's going to be down 1 over 1 gets us to this point on the y-axis, the point 0, 1, 0. And it gets us then also, draw this line now, to the point 1, 0, 0 on the x-axis. And so we've got another pyramid. Lots of pyramids here. The reason why is we're trying to not get these computations to get too nasty, so we're keeping things nice and linear so that we don't get just crazy equations that we're working with right now. So the volume that we're integrating over is that of this pyramid, right? But we no longer care about just finding the volume of this pyramid. We actually care about finding the hypervolume of the four-dimensional region over this three-dimensional space and under w equals f of x comma y comma z, which is just z. So keep in mind, we're getting a hypervolume here. So our hypervolume, h, is going to equal the triple integral from 0 to 1 of the integral from 0 to 1 minus x of the integral from 0 to 1 minus x minus y of z, dz, dy, dx. So we get the integral from 0 to 1, the integral from 0 to 1 minus x of 1/2 z squared evaluated from 0 to 1 minus x minus y, dy, dx. So we'll see how quickly this gets a little gross here. I'm going to pull the 1/2 in front of everything. So just for the sake of saving a little bit of space, I'm going to do 1 minus x minus y quantity squared, which we know we need to put in here. This is going to equal 1 minus x minus y times 1 minus x minus y, which equals 1 times 1 is 1, minus x minus y. And we take the negative x and multiply it by everything. We get a minus x and a plus x squared and a plus xy. And we'll take the negative y across everything to get a minus y plus xy plus y squared, and simplify this down to be 1 minus 2x minus 2y plus 2xy plus x squared plus y squared. Alright, so see how this gets nasty as soon as we start actually putting things in here. This is even with us just doing nice linear things in all of our dimensions. So we have 1 minus 2x minus 2y plus 2xy plus x squared plus y squared dy dx. And now we're back to our double integral situation. So this equals 1/2 integral from 0 to 1. We're integrating with respect to y, so I'm going to get a y minus 2xy minus y squared plus xy squared plus x squared y plus 1/3 y cubed evaluated from 0 to 1 minus x dx. And this is super complicated itself. So let's see. How do we want to go through this? I'm going to shrink things down a little bit. I want to keep this stuff here so that if you're looking at the static version that it still exists. Alright, so let's then look at, we're going to have this be 1/2 times the integral from 0 to 1 of 1 minus x minus
minus 2x times 1 minus x minus 1 minus x squared plus x times 1 minus x squared plus x squared times 1 minus x plus 1/3 times 1 minus x cubed dx. So we can do some factorization to make this look a little bit easier. I am literally just playing with this right now to see if I can't make our lives simpler. So let's see, if I factor out a 1 minus x from absolutely everything, I'm left with 1 minus 2x minus 1 minus x plus x times 1 minus x plus x squared plus 1/3 times 1 minus x squared dx. And then inside here I want to combine like terms. So here I get equals 1/2 times the integral from 0 to 1. And let's see. This is 1 minus 2x minus 1 plus x minus x squared plus x squared plus 1/3 x squared minus 2/3 x plus 1/3. And combining like terms, these x squareds cancel. We get a 1/3 x squared. And then x's, we get negative 2x plus x cancel, and we're left with the minus 2/3 x. Wondering if this would have been nicer to... Yeah, we probably could have combined earlier to save us a little bit of grief here. Is what it is. Let's keep plugging away. We've got 1 minus 1 cancels, and then we have the plus 1/3. Dx, I can actually pull that 1/3 out now to get 1/6 times the integral from 0 to 1 of, let's see, I'm going to have 1 minus x times x squared minus 2x plus 1 after factoring out that 1/3. This equals x squared minus x cubed minus 2x plus 2x squared plus 1 minus x, which equals negative x cubed plus 3x minus 3x plus 1. Now we're almost there. All right, negative x cubed plus 3x. I think there's squared. There we go. Squared minus 3x plus 1 dx. And this equals 1/6 times negative 1/4. When I plug in a 1, it's just going to be a negative 1/4. Oh, I'll just write it. Do this in 2 steps. So x to the 4th plus x cubed minus 3/2 x plus x evaluated from 0 to 1 is going to equal 1/6 times negative 1/4 plus 1 minus 3/2 plus 1 equals, so we're going to have, let's see, let's do this all in fourths. Negative 1 plus 4 is 3, minus 6 is negative 3, plus 4 is 1/4, times 1/6 is 1/24. So the hypervolume is 1/24. Sorry for squeezing that so tight. Hopefully you have some extra paper and can work that out. over there if need be. Like I said, these get really messy really quickly even if we have nice linear things. So let's keep that in mind as we move on to exercise 19.4.1. This is for you. Go ahead and pause the video. Here in just a second, exercise 19.4.1, find the triple integral over the region E of x d capital V, where E is bounded by the paraboloid x equals y squared plus z squared, and the plane x equals 4. So you're going to need to sketch those out in 3 dimensions to see what your bounds in the x, y, and z directions are. You can set this up as a different type of integral if you want to. In the end, your answer should come out the same. But go ahead and give this a shot, pause the video, and I will work through the solution with you in just a few moments. And we're back. All right, so I again pulled some polar coordinate stuff out here because I saw a lot of circles. We're going to get into that actually in more details on the next one. Hopefully I can kind of talk you through how I worked it out here. I did try and do this in all rectangular coordinates, and I gave up about halfway through, about 15 minutes of work, and I was like, nope, I'm not going to go this direction after doing some scratch paper stuff, even on top of what I had on the screen here. So let's back up though. Here I have x equals y squared plus z squared, and this is a paraboloid, elliptic paraboloid. So if x equals 4, because we're going between this elliptic paraboloid and the plane x equals 4, so when we do that, if I set x equal to 4 in this equation, we get y squared plus z squared equals 4. So that gives us a circle of radius 2 in the yz plane. I'd actually given you guys a clue by having the yz plane set up already here. So this circle we get when x equals 4. Now, if we're going to do the y boundaries, y lower to y upper, as the y lower equals negative square root of 4 minus z squared, and the y upper equals the positive square root of 4 minus z squared, we can do that and then do from z is negative 2 to positive 2. And that's actually how I have it set up at the beginning. I switch to polar form here after I've got it down to a double integral. Then when I set this up in the x, y, and z 3 space, then I have the plane when x equals 4. I've kind of redrawn the axes, the y and the z axes, kind of as a dotted line when x equals 4, so I can kind of then get the circle that we'd drawn in the yz plane above to go ahead and draw that when x equals 4 and label the points at the far sides and far top and bottom to be 4, negative 2, 0, 4, 0, 2, 4, 2, 0, and 4, 0, negative 2. And we know that this elliptic paraboloid is a opening in the positive x direction because it's a positive y squared and positive z squared. So we can essentially draw parabolas starting from the origin at 0, 0, 0 out to those 4 points that I just said, the 4, 0, 2, 4, 2, 0, 4, 0, negative 2, and 4, negative 2, 0. And that gives us the shape of our elliptic paraboloid. So we want to find the hypervolume of x dv over this region, capital E. So my x lower bound is going to be y squared plus z squared, and my x upper bound is 4. So I start by setting up the triple integral over the region E of x dv equals to negative 2 to 2 in the z direction, the integral from negative square root of 4 minus z squared in the y direction, positive square root of 4 minus z squared, as the upper bound for the y direction, then the integral from y squared plus z squared to 4 in the x direction of x dx dy dz. So I go ahead and start by doing this in the x direction first. So taking the antiderivative with respect to x, we get that this equals the integral from negative 2 to 2 of the integral from negative square root of 4 minus z squared to positive 4 minus z squared positive square root of 4 minus z squared, of 1/2 x squared evaluated from y squared plus z squared to 4 dy dz. Plugging in these bounds, we get that this equals the integral from -2 to 2 of the integral from negative square root of 4 minus z squared to positive square root of 4 minus z squared of 8 minus 1/2 parentheses y squared plus z squared close parentheses squared dy dz. Now that we're just in the dy dz integration, if we think of y as r cosine of theta and z equals r sine of theta, then we have our theta is going all the way around, because when we drew our region in the yz plane, we're going all the way around. It's a full circle of theta being between 0 and 2 pi, and our radius is going from 0 to 2. So I'm switching this to polar coordinates by noting that y squared plus z squared equals r squared, and plug that in for the y squared plus z squared, and when I square that I get r to the 4th, and then my bounds are switching to r's and thetas, and then we just have to remember to do r dr d theta, not just dr d theta. So this equals the integral from 0 to 2 pi of the integral from 0 to 2 of 8 minus 1/2 r to the 4th, close parentheses, r dr d theta, where the 0 to 2 pi is in the theta direction and the 0 to 2 is in the r direction. So the inner integral is all r stuff. There's no thetas involved at all, so I can switch this to equal the integral from 0 to 2 pi of d theta times the integral from 0 to 2 of 8r minus 1/2 r to the 5th dr after distributing the r through. This then equals 2 pi times parentheses 4r squared minus 1/12 r to the 6th, close parentheses, evaluated from 0 to 2. Plugging in those bounds, we get that this equals 2 pi times parentheses 16 minus 16 thirds, which equals 64 pi over 3. Alright, so that's going to be probably the best way of going through and getting this integration to all work out. You are absolutely welcome to do it in rectangular coordinates if you'd like. I just think that it's more painful than it needs to be. So let's move on and actually talk about triple integrals in polar coordinates, section 19.5. So we're going to do this again, but we're going to do it with more intention from the beginning. Example 19.5.1, determine the volume under the surface. The vector function in two variables, s of u comma v equals the vector v cosine of u comma v sine of u comma -3/4 v cosine of u plus 4 end vector, with 0 being less than or equal to v being less than or equal to 2, and 0 being less than or equal to u being less than or equal to 2 pi, using a triple integral in polar coordinates. So let's go ahead and take a look at this graph in GeoGebra. Here we have it. And the green surface, this really shows our x, y, and z values. We can see that it's given by r cosine of u, r sine of u, -3/4 r cosine of u plus 4. I switched the v to an r just because I'm recognizing right away that that v value is really the radius of this, but I could have left it to be just the same and it wouldn't have changed anything. We can see that this green surface within those restrictions is giving us this circle in our x and y directions, and in the z direction it's given by this -3/4 r cosine of u plus 4. So if I want to take this and set this up in a triple integral using polar coordinates, I recognize that this surface has x equals r cosine of theta and y equals r sine of theta, with 0 being less than or equal to 2 being 0 being less than or equal to r being less than or equal to 2, and 0 being less than or equal to theta being less than or equal to 2 pi, which is really what the restrictions on v and u are, because as we look at this, my v and my u are just my r and my theta. So this is really trying to get us
right to the x and y equals r cosine of theta and r sine of theta right away. Now z equals negative 3/4 r cosine of theta plus 4. Okay, so that's going to be our bound in the z direction. Now, by switching this to polar form, as we have here, we need to recognize that the volume is going to be given by the integral from 0 to 2 pi in the theta direction, 0 to 2 in the r direction, from the lower bound on z is just 0. We just have the xy plane here. So 0 in the lower z direction and negative 3/4 r cosine of theta plus 4 in the z direction. To do the volume, we're just going to take this with 1 times r dz dr d theta. And I just put the r on the inside because we want to have it inside all of our integrations here. So I'll go ahead now and start doing this. This is going to give us the integral from 0 to 2 pi, the integral from 0 to 2, and then we're going to have a z that pops up that goes this. Let's just do it. rz evaluated from 0 to negative 3/4 r cosine of theta plus 4. These are z values, dr d theta. This equals the integral from 0 to 2 pi, the integral from 0 to 2 of r times negative 3/4 r times cosine of theta plus 4 dr d theta. And so we can go from here, and we do have thetas and r's being mixed together, so I can't really separate things out right now, at least not as I'm seeing it. So this is 2 pi, 0 to 2 pi, integral from 0 to 2 pi of the integral from 0 to 2 of negative 3/4 r squared cosine of theta plus 4r dr d theta. And let's go ahead and go over a column here. Oops. I want to give myself a little more room. So I'll go from here to a new column. So this equals the integral from 0 to 2 pi of negative 1/4 r cubed cosine of theta plus 2r squared evaluated from 0 to 2 in the r direction, and then d theta. So this isn't working out too bad. We can now plug in 2 for my r values. The zeros will all cancel out, so I don't need to worry about that. This equals the integral from 0 to 2 pi of 8/4 is so negative 2 cosine of theta plus 8 d theta. So we get 2 sine of theta plus 8 theta evaluated from 0 to 2 pi. Sine of 2 pi is 0 plus 8 times 2 pi is 16 pi. And then minus sine of 0 is 0, minus 8 times 0 is 0, so we just get 16 pi. And that is the volume under this surface. All right, that is everything I have for you for this lesson. We're going to go into more details on triple integrals in cylindrical coordinates, which is essentially the same thing as polar coordinates, next class. And then we'll get into spherical coordinates and how to take triple integrals in spherical coordinates once we've hashed all of that out. So, hope you enjoyed listening, and I will talk to everyone in the next lesson. Have a great day.